Hello everyone. In this video, we are particularly going to discuss about silhouette coefficient and how silhouette coefficient is going to help us understand what the right value of k is. That is the right value for number of clusters for the given data. We earlier have explored more on understanding what elbow method is. That is, we have computed this within cluster sum of square distances for every possible value of k. And then we have come up with this particular plot where on x-axis you have the number of clusters, on y-axis you have inertia or within cluster sum of square distances that we have computed. And then we clearly have observed this particular elbow region. We can either consider k value as 2 or k value as 3, but we have conservatively picked up the k value to be 3. And then we have further looked at creating the final model object by considering n clusters as 3, and then generated the cluster labels for all the data points that we have considered. Later looked at the frequency distribution here. But there was one disadvantage with inertia that we have understood. That inertia or within cluster sum of square distances only understands how cohesive the given clusters is or how compact the given clusters are. It never really bothered about the intra-cluster distances. That is the distance between the clusters. So we not only have to look at the compactness of a given cluster, but we're also supposed to understand how well the clusters are separated between them. And silhouette coefficient is exactly the measure that's going to help us understand how well the clusters are separated, but also tries to understand compactness of a given cluster. In order to understand this mathematically a little better, let's consider this particular example where we have two different clusters C1 and C2. So C1 basically have this particular data point I. So for a given data point I, we are now computing the distances with respect to all other data points within the given cluster C1. So this particular distance is D1 and this distance is D2 and this one is D3. So now we take the average of all of these distances that we have computed for this particular data point I. We call that average distance between I and all other data points as A sub I or A of I. Similarly, we consider the same data point I and compute the distance with respect to all other data points in its nearest cluster C2. So C2 is the nearest cluster to C1. There could be other clusters as well, C4 and C3, but we're not considering in order to compute what B of I could be because we're only considering the nearest cluster here. So all of these distances that we are now computing, right, that is di1 or di2 or di3, whatever the naming convention is. So we take the average of all of these distances again, we call it as B of I. And now I subtract A of I from B of I. So this itself is a good indicator to understand how well the clusters are separated. Let's hypothetically consider a scenario where these are your data points within cluster C1 and these are your different data points belonging to cluster C2. And this is a particular data point that we are currently investigating. That is the data point I. We know that the clusters are overlapping here and B of I probably is same as that of A of I. When B of I and A of I are more or less same, then obviously this is going to turn out into a value of 0. So S of I is going to turn out into a value of 0, indicating that the clusters are overlapping and hence it's a poor measure. So we cannot say that the clusters are well separated here. And what if your B of I is much larger than A of I? So this here is a classic example of well separation between clusters. So when B of I is a larger value, obviously S of I is also going to result in a larger value. In order to normalize that value, in order to normalize the numerator, we have considered maximum of A of I comma B of I within the denominator, which lets the resultant values to be on the bounds of -1 to 1, right? Now in such case where B of I is especially larger than A of I, then obviously S of I will result in a value closer to 1, which indicates that the clusters are not only tightly packed, but they're also well separated, isn't it? And what if B of I is very lesser than a relatively lower number than A of I, then obviously whatever data point that you are investigating may not be assigned to a right cluster. That's what I can say, right? Because obviously you are always supposed to understand that A of I, that is the distances that you have computed within the clusters, should at least be, right? Should at least be lesser than or equal to B of I, right? So the B of I should be large enough. Cool. So since we have fairly understood on how you compute this S of I for a given data point I, and we also have understood the meaning of these different values like -1, 0, and +1, and how to interpret them. So now let us look at implementing the same in Python. So before we do this, so the resultant silhouette coefficient or silhouette score is average of all of the silhouette coefficients or silhouette scores that you must have observed when you have evaluated for all the data points. You are considering all of the data points and then you are calculating the individual silhouette scores. Take average of all of that and we call that as a combined silhouette score which can be interpreted. Yeah. Now let us look at implementing the same in here in Python. For that we are supposed to look at importing silhouette score first from sklearn.metrics module. And once we basically import this silhouette score function, which is going to help us calculate that score, right? So we now would look at iterating over a range of possible values for k. We need to have a minimum value of 2 for k because the silhouette score is taking into account the intra-cluster distance, sorry, the inter-cluster distance, taking into account the inter-cluster distance, that is the distance between the clusters. And hence, there should be a minimum of 2 clusters at least when you are trying to calculate this score. So obviously, I am going to use this kmeans class in order to create an object, create a model object. So I'm not looking at setting any other parameters here because the centroid initialization algorithm is going to be kmeans++ itself. Anyhow, I'm calling this model object as model and then directly use this particular method called fit_predict in order to generate all the predictions or predicted labels applied onto the X data, derive the predictions, use the silhouette score function, necessarily look at passing this X data as well as predictions in order to generate this silhouette score. And obviously I'm going to define an empty list first, an empty list, and then try to append all of the silhouette scores that I compute for every k value to this empty list. So it should be an empty list for the first iteration, but not for the subsequent iterations. So once I run this particular code, we now have the respective silhouette scores computed for every possible value of k that we have tried to evaluate. Now let's try to come up with this visualization where on x-axis you will have the value for k, that is the number of clusters. On y-axis, instead of within cluster sum of square distances, you'll now have silhouette scores. Okay, we correct the spelling here. Okay, so silhouette coefficient or silhouette score is what you'll have on y-axis. But here it should be SI scores and not the within sum of square distances. There's some error we need to fix first. Okay, so it has to be range 2, 10 because we clearly have understood the minimum value for k should be 2 since we are considering at least 2 clusters in order to compute the value of b of I here. Anyhow, from this particular plot, we clearly understand that k equal to 2 is having a higher value for silhouette score and hence k equal to 2 is the right value that we need to consider for us to create a final model object. When compared to k equal to 3, and compared to this silhouette score where k equal to 3, the score that we have computed for k equal to 2 is much larger, and then we can finalize this value of number of clusters to be final one. So we can later look at considering this code where we are trying to create a final model object. So instead of 3, we're now providing a value of 2. And this here is going to assign cluster labels to all of the predictions that we are having. We can simply go about checking the value counts of it so as to understand how it's distributed. So there are 100 data points now assigned to label 1 and 50 points assigned to label 0. So this is how you can interpret the result of it. Again, it's left up to us in order to determine what could be the right value of k. So I can take a reasonable decision. I can take a reasonable decision based upon the elbow curve that I have obtained previously and the silhouette scores that we have computed for different values of k. Based upon this visualization, I can clearly understand the right value of k. I might simply go about considering k value as 3 because I can be little considerate that the difference is not that high. And I also can look at perceiving the compactness of the individual clusters to be better here when I compare k equal to 3 here. So this is again the decision that's left up to the data scientist to be taken. Okay. I believe that we are pretty much clear on what silhouette score is and how it's going to help us not only cater to the intra-cluster distance, it also helps us to cater to inter-cluster distances as well. Okay. So that's all in this particular session. Thanks for watching.